So I wanted to begin this talk by discussing why someone would care about such a problem, because I think it's worth discussing that for a bit of time before we just go into the sort of the idea behind the proof. I think it's actually a somewhat of a simple idea, but it's worth talking about why someone would care about these problems. So I'm going to start by just putting up this is not the equation I'm going to talk about, or that's not the equation that my paper is on, but I wanted to talk about this one first. So you have this wave equation in 3D. So, and I'm not being too particular about if it maps all of R1 plus 3 to R. We'll just say, we might be a subset of that. And, if you're studying this type of equation,
this is a defocusing equation, right?
The equation I'm talking about is defocusing, but this one is not. This one is focusing. Yes.
Focus, yeah.
So you're sort of jumping ahead a bit in the punchline, if you will. But yeah, so if you didn't know anything about the wave equation, let's say you didn't know anything, what would you what would be the first approach to do it? Well, I think the natural approach would be to see if you could just solve an equation with 2 terms instead of 3, right? I mean, that's always what you do in math, is if 3 terms is too many. So you try to solve 2. So if you tried to solve 2, you might start by dropping the UTT term, and then you would get the Albin-Talenti function, which would be constant in time, and you would just have, you have to figure out what those constants are, but yeah, that's well known. You might have, if you drop the Laplacian, you would have this equation, and this is an ODE whose solution is c times t to the minus 1/2. If we like to, it's useful for these problems, or at least these problems generally are thought of as having data that decays at infinity in space. But that's no problem. You just take u of 1 equals chi of x over 2 times c, and ut of 1 is equal to minus chi of x over 2 times c over 2. And because of finite propagations, so chi equals 1 on x less than or equal to 1. So it's constant on the parts that the region of influence. It's going to be constant because you have finite propagation speed, and so you would end up with u of t comma x equals c times t to the minus 1/2 for t between 0 and 1, and x between, x is also bounded by 1. So this is a function that's going to blow up as t goes to 0, right, in time. And then finally you have, if you drop the u to the 5th term, you have your linear wave equation, which you know from Evans or Sog's book, lots of books that how to solve that. So this is, I think, a very important thing to keep in this paradigm, is an important paradigm to keep in mind, because these are sort of the 3 canonical examples of what might happen, or what is known to be able to happen for a solution to a nonlinear wave equation as time goes to infinity. It could sit and be constant. It could blow up in a finite time, or it could exhibit properties like the the linear wave equation. And so that's sort of the fundamental question of this, at least this problem is, can you categorize all of those different solutions for a long time? That's right. And then another, because for a short time, the linear wave equation is going to dominate in every case. But for a long time, do you have these types of solutions, or is there another type of solution that could happen that we haven't been able to find? But now, as Tom said, we were talking about the focusing, but we're talking about the defocusing problem now. Yes. So yeah. Or perhaps I should say Professor Spencer. Okay. And the defocusing problem. So we're just simply changing the sign of U, right? So we just moved it over to the other side, but we didn't bring the negative. So we've changed the sign. And now let's try. If we try to do the exact same thing as we did before, we're going to run into some problems, right? Because in some cases, because first of all, you have minus Laplacian of U plus U to the fifth equals 0. And there's only one solution that you can get for that, which is U equals 0, because minus Laplacian is okay. I should back up and say we're always interested in Sobolev, these being in Sobolev spaces and decaying at infinity. So if if you're an L2 or something, an L2 based Sobolev space, then this is going to be a positive definite operator on U, and then U to the fourth is also a positive definite operator on U as well. So the only way you can get a solution to 0, U would have to be 0, right? So that's good. Now, if you try to solve UTT plus U to the fifth equals 0, now in this case, if you try to solve your ODE, what you have is you have a function that's concave in time, right? If U is positive, your function is concave in time, so you can't have this blow-up solution. You might have, so which rules out the possibility of sort of saying, oh, you've got to blow up, and then you've got to, infinite time, and then you've got a finite propagation speed. I mean, because you'd have to, you can't directly transfer this over. But of course, if you drop your U to the fifth term, then you have a solution you still have a linear wave equation. So this is why, on this basis, there's a conjecture that this is the only thing that happens in the defocusing case. That in the focusing case, you have these three phenomena that we know happen, and there's a lot of research into trying to catalog the different things that might happen, and it's still an ongoing process. But in the defocusing case, it's good. There's a good reason to think that it would only be eventually dominated by this term, right? So let me just write it down.
So eventually, it will look like the solution will look like the solution to the linear wave equation.
Right. That's right. Because these canonical examples can't happen. Yeah, that's right. So let me. Conjecture. UTT minus the Laplacian of U is globally well posed and scattering for U0, U1 in H dot SP So, okay, so now I have to define a bunch of terms because I just put them down. So globally well-posed. So first of all, globally well-posed. What does that mean? Well, we know that an equation is, we say equation is well-posed on an interval if you have a solution that's unique, that the solution is continuous in time, and that it depends continuously on its initial data. Okay. Scattering is that we're saying that not only is the solution exist for all time, but it can be well approximated by a solution to the linear wave equation as t goes to plus or minus infinity. Now, it might be a different initial data. It's going to be a different initial data at plus infinity versus minus infinity, and you can calculate the scattering matrix and all sorts of things to see how they relate. And frankly, you'd have to ask somebody else how to do that. But the point is, you have a u plus and a u minus. Sorry. So I need to just mention something. So I started studying scattering for the Schrodinger equation, where you just have an initial data. But then I moved to the wave equation, where, of course, you have initial data and a velocity. So sometimes I just say the initial data as if it's just one function instead of two. So just know that I'm talking about a vector, okay? Just so you know. So, because I'll inevitably make that mistake again. Yeah, so scattering just, you just have u of t, comma u sub t of t, minus s of t, u naught plus, u naught minus, u1 plus. Goes to 0 as t goes to infinity, and this s of t is the solution operator to a, so it would be, I guess, you'd have your cosine of t square root of minus delta, and then sine of t square root of minus delta over square root of minus delta, right? And then you'd fill it in, right, for your solutions to, to get a vector of solutions to your linear wave equation. So finally, we have to discuss this S sub p, and in particular where that comes from. And where it comes from is that if you have a solution to this problem, you actually have an entire family of solutions. So just take v of t comma x equals lambda to the p minus 1 over 2. And this solution is also going to be a solution to the same wave equation, because you'd get lambda squareds in front of every term, so it's fine. And the norm the Sobolev norm that's preserved under this is the SP norm. And that's a really big deal, because right? Because of the scaling, and it's really very important. So in general, you have the following. Okay, so let's say you had data let's say you took a data in S bigger than SC. Well, we know from any PDE, really, that probably any PDE, maybe there's some exceptions, but We like small data, or we like small things better than big things, right? I mean, that's always true. Almost always true. I don't know. Maybe someone could probably tell me an exception to that. But we usually like small, right? And so suppose you want to make your data small. And you can't, changing the lambda. Well, you can't do it if your S is equal to SP, right? Because it's always going to be the same. But what if you had S bigger than SP? How would you make your data small? You would take lambda small, right? And then V is small. So then that means that solving on the time interval t less than 1 with small data is equally as hard as solving the problem on a small interval with large data. And that's a very, what we know from evolution equations, that's a very just and equitable trade-off, right? It really is a very, very fair in some ways, right? Because, okay, you either get small data or you get to do it for a short time. But now suppose you have S less than SC. Now you would need to take lambda large. And then that means that T small and small data is just as difficult as T large for large data. So there's a whole series of results for data below the critical scaling proving that you have to have ill-posedness. So there's a result by Lindblad and Sogg for the wave equation. There's results by Tao and Christ and Colliander for the nonlinear Schrodinger nonlinear KdV equation. And what they use is essentially the idea that you can take big problems, right? You can take big problems, things the phenomena that would occur at large time for large data, and hide it at very short times and in very small data, and then at a limit, you end up with something that's ill-posed. It's not even continuous past time equals 0. So that's all I'm going to say about that. So
what kind of results do they have that you were mentioning about the ill-posedness? What are they?
Well, they show that it can't be continuous, that there is initial data.
Not for this equation or for which equations?
Well, you have to have S, if you're in S with S less than SP.
Oh, okay.
Yeah.
Then they prove that's ill-posed.
That's right. That's right. But if S is bigger than SP, then you know that you're okay. Then you're in a completely different situation, and then you're okay. And that's why we care about the data at SP regularity is what I'm finally trying to say. And to end result then is to get to the topic of the talk, which is something I proved actually right when I got here. The equation, let's call this that's our equation, is globally well-posed and scattering for U0, U1 in H dot SP cross H dot SP minus 1 radial 3 less than or equal to P less than 5. So this is at least partially discussing that conjecture. Right?
Well, it's really a borderline case in some sense, right? Because if you made your S's smaller than SC, then it's not true.
That's right. And if you made them bigger than SP, you would know that you had local well-posedness on a specific interval. So, yeah, that's right. So, because you could use this type of argument, right, to say, well, to make it small.
That wouldn't necessarily tell you
No, it won't. That's right, it won't. So this is really the space, that's why this is really the space that you want to work in, if you can, I think, because then you can get scattering, which you wouldn't be able to get even if you could guarantee that the S norm was bounded for all time, let's say. That wouldn't give you scattering. It would give you well-posedness, but it wouldn't give you scattering.
So I take initial data, which is much more regular, let's say, compactly supported, then I don't, was scattering known for that data?
Well, compactly supported it was, because you have the results of Strauss. Yeah. And that's right. So you have the results of Strauss for compactly supported, and even for data that had some kind of nice decay properties. It had to have good decay, yeah. And so then it was in a lot of spaces, right? Because it was smooth and it had good decay at infinity. Yeah.
So this is a much bigger space.
Yeah. So it is the space that we want, except for, but only that it's radial. That's the only, and that is a real problem with the. I mean, with the argument wouldn't just work for non-radial, and I'll hopefully it would at some point work, but not yet. And I think it's actually, well, anyway, maybe I should just keep going with the lecture, and we can talk about it in a bit. But we can talk about what to do next. But oh, someone dropped the chalk back there. Yeah, so let me. So, yeah, so let's press on. So we have the conserved quantity for a solution. And what this means automatically is that so you'll notice from your S sub p that S of 5 equals 1, right? And S of p is less than 1 when p is less than 5. So why that's important is because when p equals 5, then you end up with the energy 1/2 you end up with an energy that's at the critical scaling, right? So you have a conserved quantity at the critical scaling. When p is less than 5, if you knew that you had finite energy, that would be enough to give you a global solution, because you would know that the H1 norm was bounded, and then just for any local in time result, you would just use this type of rescaling. But you wouldn't be able to necessarily do that when p equals 5, right? Because the rescaling argument wouldn't change the size of the data. And so p equals 5 is a much more was a much more delicate issue, because that was worked out before all of this. But let me circle back to what I was. Let me try to follow my notes more closely so I don't forget what I talked about. So we had if you recall, our three definitions we had our three canonical examples that we talked about at the beginning. We had Albin-Talenti function, and then we had the ODE blow up, and then we had the linear wave equation. You could notice that the Albin-Talenti function preserves the H1 norm, right? I mean, it's constant, so it preserves the H1 norm, whereas the ODE blow-up type solution does not. It has the H1 norm going off to infinity. And so because of that, and then there's also the possibility of scattering. So there's two classes of non-scattering solutions. And those are called type 1 and type 2 blow-up. So and type 1 is that the critical SP Sobolev norm is unbounded. And then the second one is the critical SP Sobolev norm is bounded. So for example, the Albin-Talenti function would be considered blow-off, even though it just sits there and doesn't do anything, because it's blow-up in infinite time, because it doesn't show that kind of scattering behavior that you would want to see. And you can have, at least for some dispersive PDEs, you can have blow up in finite time, but the critical norm doesn't blow up. But then you can also have the critical norm being unbounded, and that clearly doesn't scatter, right? Because the scattering norm is a unitary operator, right, of the wave equation. So the p equals 5 case was a topic of great interest, and the reason for defocusing and focusing, but the reason for at least for the defocusing, why it's so important, or why it was so interesting, I think, is because there's no type 1 blowup, right? Because you have your energy E equals 1/2 integral u to the 6th, and if you know that your H1 norm is finite, then that energy is going to be finite, and therefore the H1 norm has to stay finite for all time. So we know we don't have type 1 blowup in the p equals 5, but type 2 was not such an easy, is not an easy question. It's not simple, but it's been worked out. It was worked out maybe starting in the early 90s, I think. It was Gralakis' work. And then you had, so let me just, Strua, yes. So let me read out so it was Ginnebre, Strua, or Soffer and Velo, and then also Strua for the radial case. And then you had Bahorian, Girard, Gralakis, Chatat, and Strua for the non-radial case. So that was a very important breakthrough in the field of dispersive PDEs. And then I should mention also then that argument was taken then by Bourgain for the NLS and Tau and the I team and many others in the nonlinear Schrodinger equation as well. But to show that the no type 2, you're essentially trying to show some kind of non-concentration type argument. So in other words, if the critical Sobolev norm is bounded, but you have some kind of blow-up phenomenon in finite time, then it must concentrate on a backwards light cone at the tip of a backwards light cone. And then Gralakis was able to show, well, that can't happen, and therefore it must be global. And then moving on to proving scattering requires the profile decomposition and concentration compactness type arguments. And you could, I'm sure people, yeah. It's a very important argument, and I think well worth spending a lot of time thinking about.
So if the norm is bounded, what does it mean to be blow-up?
Well, it just means that you don't, so like the Albin-Talenti function is considered a blow-up function. Even though it sits as a constant in time, that's considered blow-up because it's not scattering.
Anything that's not
Yeah.
scattering is blow-up.
That's right. That's right.
So it has to go to zero the way the wave equation does.
That's right.
The solution to a wave equation does.
That's right. So yeah. So
We've
that.
done some scaling so that it looks like blow up in some way. Of course, it's not blowing up.
Yeah. I mean, I guess. Yeah. I don't know. Could you make some kind of? I mean, I know for the NLS, you can take a soliton and turn it into a finite time blow-up solution by using your conformal compactification. I don't know that you can, if you can or cannot do that for the wave equation. That's a good question. I don't know. Yeah. So anyway, that's right. So so we're in the for this problem for this paper we're in the case when we're energy, we would be considered energy subcritical. So 3 is less than or equal to p less than 5. If you want energy supercritical, there's the work of Becchianu and Soffer, the work of Boulout, Killip and Vishan and Krieger and Schlag. There's lots of work there. And that's really a very different issue. And so I'm not going to.
So what do they do that's different? Sorry.
Well, so you have, well, for example, showing that there's no type 2 blow-up in the energy critical, supercritical problem. And then then there's also some work recently for certain initial data that are special in some ways, but are in the, or even in some cases not in this specific Sobolev space, but you can guarantee that you have scattering, even if it's large. So for this, and then what in 3 for this range previously, there's some work of in also type 2 blow up as well. So there's the work of Rupang Shen for 3 less than p less than 5 when it's radial, and then Andrew Lowry and I did the p equals 3 case, and then recently Mendelsohn and Lowry and Murphy and I did the non-radial case for 3 between p and 5 if it's type 2 blow-up. But that still left the question of type 1 blow-up, which is what I want to talk about just now. So this argument comes from the argument of Bourgain for the Fourier, called the Fourier truncation method, and then it was used by Koenig, Ponch, and Vega. So Bourgain made it for the nonlinear Schrodinger equation, and then Koenig, Ponch, and Vega used it for the wave equation. So what we're going to do is we're going to take a solution, and we know we have a local solution. So we'll take a solution as long as we can, and we'll split it into 2 pieces. Now, and we're also, remember we have our scaling that we have, and we're going to use that scaling, and we're going to use it to rescale the data so that this is small. So we want this to be of size epsilon, which we can always do, right? We can always spread it out as much as we have to get it to be at low frequencies, and then. So because it's small, then you can use you can brutally apply your Strickhart's estimates to this and solve W, right? Because it's small data arguments, that's easy, right? Because then you get a W cubed for your nonlinearity, so it's very easy to approximate it with a linear solution, right? Because then this is of size of order size epsilon, and then you've got an error of size epsilon cubed, and you just keep on going, right? Now, and if you didn't have these 2 terms, either. If you didn't have any cross terms, then you'd be done because you'd be in The other part would be have finite energy and therefore automatically have a global solution. But we have these cross terms that we have to deal with. And this is where the radial symmetry comes in, because we have these results of Sturbens, Jacob Sturbens, for radial solutions to a linear equation, which are better than the usual Strickhart's estimates. Because what you don't have in the radial case, you don't have these sort of wave packets that kind of run off in one direction. It has to disperse equally in any direction. And that gives you better decay, some better estimates than you would normally be given. Yeah.
Could you remind me what the P is? Is it a Fourier projection?
Yes. Yes.
Fourier projection.
Yeah. Yeah. So, yeah. So, in particular, you have the following.
So now why? Sorry.
Yeah.
Okay, so why, if I didn't have the coupling, would everything be easy?
Well, this would be small data, and so you would use the Strickhart's estimates, and then you would just sort of, yeah. And then here you would have finite energy, so you would be guaranteed to have the energy conserved, and then local.
You got the projector.
Yeah.
Now, when you the projector, yeah. So. Okay. Yeah.
Yeah. So just to point out that when P is not 3, then you have it's a bit more difficult, right? Because you don't have this nice sort of splitting. But this is a talk, so you don't want to. Yeah, you don't want to talk about it. It's not something you want to do where someone might see you do it, make a mistake in real time, because you probably will make a mistake in real time, right? I mean, at least I would. Some people might not. So we have this, and then we also have a nice result from Sturbens, and it's not even. I wouldn't even say it's explicitly mentioned in his paper, but it's there. It's there. So, yeah. So we have these two. And then, so we just apply Bourgain and Koenig, Ponch, and Vega's Fourier truncation argument. So we take the energy of V, and probably going to get the sign wrong, but it's not that important. It's not important at all, actually. But might be a plus and minus. Okay, so this is our change of the energy, and we'd like to bound the energy. We can't expect the energy to be constant, but we could expect it to be bounded. Well, look. Let's say you did a really good job and you got rid of that term. You I don't know. It's not possible, but let's say you did. Then what is your V sub t? This is bounded by W's L6 norms squared times v L6 times v sub t L2, and then this is bounded by, well, this is bounded by the H1 norm, right? And then this one's bounded by the L2 norm, and so this is bounded by the energy of V times W L6 squared. But we know that integral of W L6 squared dt is bounded by epsilon squared, right? Where we're calling this epsilon, right? The size of our initial, of W naught is of size epsilon. So that's great. That's really great. That's Gronwall's inequality, right? And then you've got E is bounded for all time. Now you've got this other term that's the worst term, right? And but you can do it, and try to at least try to do it. And so let's take this one. So this is bounded by, well, we could bound it by L infinity v sub t L2 L2. We could do that. Now, this one, so this is bounded by, well, let's, let me see, how could I don't want to, yeah. So let's say we bound it by a delta plus 1 over delta and now we have that the 1 over delta. So let's see. Do I want? Yes, I do. So let's take, we have this estimate, right? And we want to use it. I don't want to get into too much. Let's say we're going to take R equals 1 over a power of the energy. So we take an interval 0 to t. We do a bootstrap argument. We take an interval 0 to t where the energy is bounded, and then we just show that the bound is controlled by a function of the time, right? So we'll do a bootstrap argument. We have an energy, and then we bound the energy by, we take R to be 1 over the energy. And then the other piece is, you've got still a piece left over, right, which is going to be inside that. But that's, I mean, you could take a big power of the energy if you wanted. So you've got some gain there for that. So I won't get into what you do there, but I can tell you later if you want. But suffice it to say, you get an advantage, right, because you've got a big power of the energy. You can put as big a power energy as you want in the denominator. But you have this term here is bounded by something whose integral from 0 to t of x to the 1/2 w L infinity squared is bounded by 1 times the natural log of capital T plus the natural log of the energy of capital T. Let's say the energy is always increasing. There's no reason not to make that assumption, times the energy, So we end up with something where we have a d by dt of e of t heuristically is bounded by natural log of e of t times e of t times an epsilon squared over delta. And that is also, you can use Gronwall's inequality. You've just introduced an e, and a natural log of e, and that's still okay. You know, you don't want a natural log of e squared, but a natural log of e is okay. And so you end up with this, you're going to, and then you also have your natural log of t in there too that has to be, so you've got something that's going to, you can only prove the energy is you can prove the energy is slowly growing, right? But you can't prove it's uniformly bounded. It's slowly growing. And then this term is actually a term that arises in the Morowitz estimate and is also bounded by the energy. So and you've got your nice delta here to squish it down, right? So you can. So what I do is I add that to the energy, the Morowitz potential to the energy. So I have a modified energy that's approximately equal to the energy, but is, you get out these nice, you can cancel out these error terms. You can cancel out this term, and then you've got some error terms that arise from that, but they're very similar in nature to the error terms. They're very similar to this. So that gives you global well-posedness. Now, if you want to prove scattering, and I don't think I have time to get into this, but I'll just, you have to then go.
Can I,
yeah, maybe that's.
You use, in your title you had radial. Where's radial?
Oh, well, radial's all over the place because you won't get these estimates without a radiality. Yeah, you're not going to get that because this is a, if you took Jacob Sturbentz's work, he has a 2D result without the x to the 1/2, but then you can, you've got that radial symmetry to go from 3D down to 2D, or there's other ways you can get that result.
These estimates are all I thought maybe the first one too, or just the Sturbenz estimate?
No, the first one too, because he's using the fact that it disperses equally in every direction to get that. So I think they're both pretty dependent on radiality. It's somewhat disappointing, but because look, with our result for the type, the result I had with Andrew Lowry for type 2 blowup, and then the result we did then with Mendelson and Murphy, we had to deal in that non-radial case. We had to deal with the hardest case was what happens if you have this solution that sort of travels along the edge of the light cone, and that's something that you don't have to deal with for radial, because it would have to fill out the light cone, and that's much nicer to handle if it fills out the whole light cone, as opposed to if you have something that just kind of travels along beside the light cone. So to prove scattering, then we have to use the conformal symmetry, and that's goes back to Strauss, in his paper where he proved scattering for the nice decay. Now here you don't have nice decay, but you have that it's small outside of, if you get away a certain distance away from the center, and so then you can use your small data arguments to solve outside the light cone, and then work in the conformal coordinates inside the light cone, and that's enough to give you scattering. And that gives you scattering for that, and at the end of the day, that proves that any initial data has a scattering size, but there's no uniform bound even in h1/2, so you have to use a profile decomposition to finish the proof to show that the bound is uniform for any size.
So what's the profile decomposition?
So it's that's fine. So it's just saying if you take a sequence of initial data, you can write that as a sum of j equals 1 to capital J s of t minus t sub j times some group acting on T and G. The group that's of scalings and then of course if you have non-radial data, you have additional symmetry, but phi j plus a remainder, and then that remainder is going to go to 0 as j goes to infinity in some sense. And then, so in other words, it sort of decouples into this solution that's, these decoupled initial data. And then you can show that on each one of them, so then you'd have to have a solution, you'd have to have this converge, the scattering size of this would have to converge to something. And then therefore you have a global bound on your scattering size, but you can't say anything about the size. So Tal took the results of Gerlachus and so on and so forth, and he explicitly calculated out the scattering size for the energy critical problem, and he ended up with e to a bunch of several exponents. But this is even worse, right? Because this doesn't even say that. It just says it's something. But it's finite.
But how do you use this to get the scattering then?
Well, so you because if you have that for each initial data you have you have a scattering size that's finite. It has to have a finite L4 node. So take a sequence that goes off to infinity, or that gets as big as possible. The biggest goes to the maximizer. Then you have a profile decomposition, and for each one of these initial data, you also know that you have a solution, and then there's a remainder that goes to 0. So it has to converge to some. So the scattering size has to converge to something. Although it could be. I'd be interested if someone could actually calculate a explicit bound, but I'm sure it would be horrible. but perhaps it could be done. I don't know. So I guess I've used up my time. So thank you for listening.